Well, thank you all for having me back, and thanks for joining virtually. I got to warn you, I've set an alarm. This is a talk that I give that normally runs upwards of 90 minutes. So to spare you, I've set a timer. If you have questions, please pop them up. I'll monitor Q&A as best I can. If you need to get a hold of me, here's my contact information. I am the MySQL Community Manager for North America. And first thing I have to go over is the Oracle Safe Harbor Agreement. I am talking 99.9999% today about the free to download license to the GPL version 2 MySQL community server and community software. However, if during question and answer, I go off in tangent on a future product, this is the legalese saying take that with a grain of salt. I don't have perfect knowledge of what's coming up. So we'll get past that real quick. By the way, if you're running MySQL 5.6 next February, I believe it's the 5th or the 6th of February, MySQL 5.6 reaches end of life status. No more bug fixes, no more support. You are officially running dinosaur equipment. And as someone who loves vintage cars and vintage guitars and vintage motorcycles, believe me, the older the things are, the harder they are to get repaired and to find parts for. Plus, it gets harder to find people who know how to work those old versions. So if you're running 5.6, please update. By the way, if you're interested in trying the MySQL database service, you can get $300 in credits free. Just go to that website and you get a full version of the MySQL Enterprise Edition, which means you get enterprise backup, the encryption stuff and all that. $300 with one or two instances will last you quite a while. And so what is this session about? Well, very rarely do I ever hear anyone complain that, this database is just running too darn fast. My applications just can't keep up. Speeding up queries, if you follow certain websites, which I won't name, Stack Overflow, you'll see that a lot of folks see it as a dark art. It's not a dark art. It's kind of a misguided science, but it's not a dark art. The understanding how to speed up queries is often seen as magic, but it's really not. And we're going to look at the proper uses of indexes, histograms, locking options, and some of the other ways to speed up queries. One of the problems that I see is that this is a very dry subject. I mean, we're talking stack dump tracing dry for assembly language level stuff. Very, very dry. If you don't catch it the first time you walk through this, this is recorded, watch it again. The slides are online. By the way, the link down at the bottom in red is where you can get the slides. I also just tweeted it. Also, this is a presentation with lots of text on screen. I'm sorry, there's really no other way to give this information over. If I could do it with sock puppets, I would. Now, something else we're not going to cover today is system configuration of your OS. I'm not going to cover the configuration of MySQL. I'm not going to talk about hardware. There are wonderful talks out there on hardware. Things like disk buffers that lie to you, throughput channels that aren't quite working the way, and also networking. If you're doing a lot of replication and you're also running DNS and LDAP services on the same network segment, your database is occasionally going to have problems that aren't really related to the database, but it'll be blamed on the database. Also, not talking today about normalizing your data. In the relational world, you want to set up your data with minimum redundancies. And by doing this, you have it in manageable chunks that work with set theory, thus relational calculus. And believe it or not, the math actually does work. Unfortunately, can't go into that today because we only got 30 some odd minutes. And what I'd like to emphasize is that you can't build a skyscraper on a sandy beach. It's just not going to take the pressure and it's going to collapse on you. For normalization, I recommend third form or normal. I am now recommending using JSON columns for stubbed information. If you have to make multiple dives to get your customer's billing address, for instance, you might want to slightly denormalize by using a JSON column. Also, think about how you're going to use your data. If you're recording a whole bunch of sales from cash register data and you're going to do time series analysis, that's going to be a little bit different than if you're going to go back and do some transactional analysis. Once again, don't use a fork to eat your soup. By the way, badly normalized data will hurt the performance of your queries. No matter how much training you give it, a dachshund will not be faster than a thoroughbred horse. Okay, the optimizer. Consider the optimizer the brain and nervous system of the database. It wants to look at your query and try to figure out the fastest, most inexpensive way to get your data to you. The trouble here is that this is quite a complex problem. There's lots of academic papers come out on this every week, and most are built on a cost model. That mathematical cost model is based on basically disk reads, because that used to be the slowest thing in the entire chain, and that's what we're still using it for. And there's some advances in that, but that's a little too crazy for this talk. Now, the optimizer wants to look at every option. You give it a query, it tears it apart, and it says, okay, I know where this piece of information is. I know where this piece of information is. What's the shortest way between them? And it's kind of like a GPS positioning, GPS in your phone or your car. It's built on historical statistics. These statistics are great, but if I want to go to the local, my local favorite restaurant, it's left out of the driveway right at the end of the street over the railroad tracks, and the restaurant's right on the left. Well, my GPS doesn't know that the train's parked across its tracks, doesn't know that the guy 2 houses down had a water leak and flooded out the road. So historical information is great, but it doesn't always help. If you're adding a lot of data or changing a lot of data, the optimizer can easily get confused. By the way, MySQL wants to optimize each query every time it sees it. There's no locking down the query plan like in Oracle. Later in this presentation, look for optimizer hints if you want to see how there's a way kind of how to do that. Oh, by the way, I will teach you how to look at a query plan and how to get it. So if your query has 5 joins, the optimizer has 5 factorial or 120 different options just for the joins. That doesn't get into anything on the right-hand side of the where clause. So if you have 120 different ways you can assemble that thing, you have the ultimate IKEA/Lego nightmare. But there are heuristics that the optimizer follows. Now for you, you're going to end up using something called explain. Now, explain is something that I could teach in a 2-week class and kind of get the major highlights on. In 5 minutes, I'm not going to be able to get to too much, but I'll kind of give you the oversight. This is the syntax of explain. By the way, that's our new shell on the right-hand side, which has command completion and wonderful help section there. By the way, if you go through the MySQL manual, it's worth reading chapter 8 if you're trying to figure out how to get a handle on this. It explains a lot of it in detail. There's some books that I'll mention later that are worth pursuing. Now, the trouble with explain is there's different types of explain. We have straight explain, explain with different formats, explain, analyze, and visual explain. This is an example of running explain on a query. Hopefully you can see my mouse bouncing around here. Put explain in front of the query. Explain select from select star from the table city where country code equals GBR. That's my actual query. Over here are the details that the optimizer gives back from explain. It's saying, well, we're hitting the table city. We have a reference in here. The reference is to country code equals GBR. Possible keys we could use or indexes is country code. By the way, that index length is 3. We'll get into why the length count is important later. Filtered, we'll go into that a little bit later. But down here is the actual query plan where the optimizer takes what you gave it up here and rewrites it so that the database can return what you asked for. Once again, if you don't get this the first time through, watch again, go through the slide deck, play with it. Visual Explain comes with MySQL Workbench, which is another free tool that we have. And that's basically the same information, just in a graphical format. By the way, green boxes usually are good. Red boxes mean you have to have a little bit of concern. Well, we also have tree format. This will tell you that this is a slightly different query. It's using something called a hash join between 2 tables. In this case, we're going to have the table city joined to the table called country, and we're going to mash those together. And this is coming back with some information on the relative cost of the various optimizations or the joinings that we're doing. Format equals JSON. This gives you even more information. I don't think any of you are probably going to want this level of information, maybe in a couple of years, so it's nice to show you that it's here. Once again, it tells us the table we're going after, the number of rows it's going to have to scan. Over here, it says we're getting a hash join, the read cost, the evaluation cost, prefix cost, data read per join is going to be 6 megabytes. So the information's out there. It's just learning how to decipher it. Now, something we did add in MySQL 8.0.18, by the way, the latest is 8.0.2.2, so this has been out there for a bit over a year. Normally, explain uses historical information. Explain analyze actually goes out and runs your query. So big warning, if you have a big nasty analytics query that you think is going to run for a couple hours and suck up all the memory, probably better to avoid this during business hours. So explain analyze goes out there and runs the query and comes back and gives you the actual time. By the way, if you are playing with explain and explain analyze and know a big variance between actual time and the time that the estimate is, run explain analyze on the table and double check the indexes just to make sure they're not mismatched in size or data type, and that should clean up things a bit for you. So more on using explain later. On to something else even more fun. Indexes. Oftentimes you see people throw indexes at a database because they've read somewhere that indexing makes everything faster. And indexes do let you track down things faster. However, there are some problems with indexes. There's some overhead, and often people apply indexes poorly. Let's see, nothing on the QA right now. So think of the index as a table with shortcuts to another table. So someone comes and looks up the vehicle identification number of your car. That's an index into another table that actually has the real data on your car. So the index is actually kind of a small junior version of the table. By the way, the more indexes and tables you have, the more this database wants to have them in memory, and the more memory is taken up. By the way, if you've never heard this before, databases love memory more than a faster processor. So memory is where you spend your money. So MySQL has many types of indexes. Once again, this is the syntax for creating indexes. We have unique, full text, spatial, a whole bunch of qualifiers, algorithms, block sizes, whether you want it to be a B tree or a hash, but that's kind of beyond the pale for today. So let's create a simple table with a primary key. MySQL's main storage engine, InnoDB, prefers to have a primary key. If you don't specify one, it will pick one. It will make up a dummy one, and I can guarantee you it will not be performant. So pick your own primary key. So we have a simple table here, table called T1. We have 3 columns. The first one's an integer. We're saying it's not null. I'll go into null later. We're going to auto increment. So every time we input a row of data, it's going to take whatever the previous value was and increment it by whatever you set it to be, usually a 1. And we're going to call this our primary key. So this is how we're going to look up most of the data on this table. And then we have 2 other columns. Now, an index is a list of keys, and you'll often hear them used interchangeably, which can kind of get confusing. But there is a slight difference, but in the MySQL world, you can kind of use them interchangeably. So don't worry about that if you see key and think index or vice versa. Now, the primary key is one that's hopefully uniquely defined for a row and should be immutable. You don't want to go back and move stuff around later. As I mentioned before, InnoDB wants a primary key very badly, and please don't use null values. I'll get into that another thing. Also, it wants the numbers to monotonically increase. That's like going 1, 2, 3, 4, 5, or 10, 20, 30, 40. If you really, really love UUIDs, which do not monotonically increase and are kind of a waste of space, we have a function called UUID to bin, which will let you work with MySQL efficiently. So something else you can do is you can actually index on the prefix of a column. Sometimes getting right in the rough area is close enough. Say like you have last names that are 75 characters long, but you do some analysis on that and you find out that 99.9% of your customers, after the first 10 characters, there's very little things that aren't unique. You might have 5 von Bluchensteins, but if you get the von Bluch, you're pretty good close to the records that you want. So in this case, we're going to create an index part of name on the customer field, and we're going to only use the first 10 characters of the name column. You can also have multi-column indexes. In this table, we have columns for last name and first name. So we're going to create an index, last name, then first name. So to use this column, we can search on last name and first name or just last name. It won't work on just first name. It kind of works left to right, so put the highest cardinality index on the first field. If you're using year, month, day, that index will work on year, month, day, year, month, and year, but not month, day, or just month. By the way, if you have questions, pop them up on Q&A. I'll check on that when I can. Hashing values. Sometimes you have data that just doesn't quite fit that mold. So what you can do is you can concat. In this example, we're concating two values and using an MD5 hash. Sometimes things just don't work out the way you want. Also, you can have things called a covering index, where the index will cover all the values you need to return a query. You don't actually have to dive into the data table itself. I mentioned that a little bit before I went to the slide. Unique indexes, there's only one value per row. Full text indexes, if you're doing text searches, we can do with an ODB a full text search. That's pretty interesting. One of the interesting features is you can actually say the first word that you're searching for has to be within X numbers of the number of words of the second one. Secondary indexes. This is you have your primary index and you have something else in that column you've indexed, maybe the customer zip code. Well, that secondary index will actually point to the entry for the primary index entry for the table. And spatial indexes, these are actually R trees for GIS type data. Very interesting, but not what we're covering today in detail. Also, we have functional indexes. Here's some examples. Functional indexes are the result of some sort of function. So if you want to round up to the nearest 100 to be able to give people price cost breaks, or you want to sub two things, like the second example here, call one plus call two. So that's the cost of goods sold and the shipping cost. So you have a rough idea of what your costs are. Multi-value indexes came out fairly recently. With the JSON data type, we had a lot of people putting in very extensive JSON documents with arrays in there. And before multi-value indexes, every index entry could only point to one row in a data table. Well, with all these arrays, that didn't quite make sense. So with multi-value indexes, you could now have more index pointers than rows. And in this example here, we're looking for the value of 3 in that JSON array. By the way, that really pays off above about 20 million rows. The speed is just absolutely amazing. So MySQL has two main types of index structures. The balanced tree, which you see on the left there, values 0 to 40 here, point off on this left branch, and that's further broken down. It's a binary search. It's worked well for several years. Hash joins, basically, they're more efficient than the traditional nested loop join that MySQL is known for. You'll see a lot of your queries once you get running, I think it was 8.0.18, 8.0.19 era, just suddenly start running a lot faster because the hash joins are automatic. Now, please keep in mind, the optimizer is a complicated piece of software, but some of the heuristics are not exactly enlightened. If there is a choice between multiple indexes on joining tables or searching for something, MySQL normally grabs the index with the smallest number of rows, and hopefully thinking it's the most selective. MySQL can use indexes on columns more efficiently if they're declared as the same type and size. So compare apples with apples, bananas with bananas. Varchar and char are great, but doing varchar and say a real value or a decimal, it's going to have to be cast, and each row is going to have to be cast. So you can see where that adds extra complexity there. By the way, check your string collations and character sets. For instance, if I'm doing something with UTF-8 MB4 and I'm combining it with Latin 1, it kind of gets messy. Things have to be set up and evaluated separately. It's just not an easy comparison. Okay, null. Back in the early days of structured query language, they wanted a way to represent that they didn't know something. So they came up with the idea of null. The old binary trick was 0 for false, 1 for true, and don't know null. Great idea. The only trouble is null has kind of some nasty side effects. This is a nice visual example of what null can mean to a lot of folks. It's not exactly true, but it's cute. So if you have a column that you're indexing and you have a whole bunch of null values in there, it's kind of like you go through the kitchen looking for a knife and you know it's not with the rest of the silverware, and you eventually have to get down to the junk drawer. And between pulling out the flashlights holding dead batteries and that old strip of Velcro that you're going to use for something, somewhere in that junk drawer are your null values. So they're not very efficient. So please avoid nulls in your primary keys and your indexes. Invisible indexes. This is something when I heard about, I thought, that's kind of a weird idea. What is an invisible index? Well, in the past, if you were trying to figure out if an index was helping you, what you would do is you look at that index and say, I don't know if you're a good index or not. You'd run explain on your query. You'd remove that index, just delete it. Run explain. And while you're looking at the output of explain, you get phone calls, texts, screams from down the hallway, especially from a power user about their query suddenly running very slowly. Guess what? They're using that index. Well, you decide that you need to get that index back, and it can take seconds, minutes, hours, days, hopefully not longer than a couple minutes, but sometimes it takes longer to rebuild that index. Well, after invisible indexes, what you can do is look at that index, say, I'm doubtful about your use, run explain, make the index invisible. The optimizer can no longer see that index. It's a server-wide blank out of that index. Rerun explain. Suddenly you start getting the text screams from the power user about the slow query. You make the index visible again. Power user's happy. Everyone goes along their way. And you start blaming it on the network, JavaScript, GDPR, Slack, or the cloud. By the way, the sys schema, which is something you can look up using MySQL Workbench, will show you which indexes have not been used and are candidates for removal. They'll also show you queries that are running without indexes that are candidates to be indexed. For the removal ones, I always urge caution. Make a big backup or two before you delete them, and I recommend turn them invisible. By the way, after a reboot is not a good time to look at the statistics, because the statistics are historical and get wiped out after a reboot. So if you see an index that hasn't been used in 2 weeks, maybe because it was after a reboot. By the way, some indexes are out there that are only used once a quarter or once a year, so be careful before you blow anything away. How to use invisible index? Real simple. Alter table, table name, and name the index and make it invisible. Then if you want to turn it visible, it's just reverse. Histograms. This is something that came out with 8.0, so it's been out here since April of 2018. They're kind of a different way of looking at things, kind of the other end of the spectrum from indexes. And no, they're not gluten-free or keto-friendly. This is a histogram of the heights of 10,000 US females. As you see here, the height tends to center around these two values and peak off at about 3,000 women at, I'm guessing that's 165 centimeters. So Wikipedia says a histogram is an accurate representation of the distribution of numerical data. This means the optimizer knows where your data is. If it doesn't have the statistics, it kind of has to search around and find everything. So the histograms help the optimizer find the most efficient query plan to fetch the data. Now there are two types, singleton and equiheight. By the way, a histogram is going to divide up your data into logical buckets. And histograms are primarily useful for non-indexed columns. If the data doesn't churn a lot or doesn't churn at all, I'd recommend using a histogram over an index. By the way, every time you update, delete, or modify an index entry, there's overhead there. And if you have several indexes on a table and you're doing lots of updates, things can slow down there. Histograms don't have that. And that's kind of the reason there. By the way, occasionally the optimizer will make index dives to double check the statistics on indexes. The system does not actually double check with you to make sure if it's okay to do that just after you left for lunch or go home for the long weekend. So index dives happen when you don't expect them, and they can impact performance. Okay. Occasionally the optimizer fails to find the most efficient plan and ends up spending a lot of time executing the query that is necessary. Oh, I need to go back on histograms. The two types, equi-height. So like you have 100 entries and you set it up in 4 buckets, you know that each of those 4 buckets is going to have 25 entries. Or you have 36 entries and all the entries are alphabetized. So you know that all the entries that start with an A are going to be in bucket A. So the optimizer assumes that the data is evenly distributed in columns, which might not be true. There's all sorts of interesting data analysis tools that go along with this. So the optimizer often doesn't have enough information on, how many rows are in each table and their distribution. So once again, the two types of histograms, equi-height, one bucket is a range of values. Once again, we have an example here of having people line up A to G, H to L, M to T, U to Z. Singleton, one bucket represents a single value of that. So here's an example of doing a frequency histogram. We're going to have 3 buckets, 101, 102, 103. Don't happen to know what happened to 104. We're going to insert into a table 2 101s, 3 102s, and 1 104. So if we do a select from our table, we see that we have the 2 101s, the 3 102s, and the 1 104. And we create a histogram with 3 buckets. Now the optimizer knows that if we're looking for something that has a value of 101, it's going to be somewhere in the first third of all the data. If it's looking for something that's 101 or 102, it knows it's going to be somewhere in the first 83% of the data. And anything with 104 is going to be in the first 100% of the data. By the way, this is a singleton histogram. Now, looking at the statistics of this, the cumulative frequency, we know that 101 is 33% of our data. And we know that 102, the cumulative frequency is 83%, even though it's only 50% of our data. But this gives the optimizer a better chance of finding your data very quickly, very efficiently. Easy to create and remove histograms. First example here, analyze table, update histograms on columns C1, C2, and C3, each having 10 buckets. And we can also come back later and redo the histogram on C1 and C2. And we can decide that we don't really need a histogram on C2. So these are 3 different histograms on 3 different columns. If you want information on histograms, they're out there in our information schema. They can tell you the table name, the population, the data type you're looking at, and the bucket count. Now, where histograms shine, you'll have to forgive me for giving this kind of elaborate demonstration. We're going to create another simple table. We're going to have in that table 2 values of 1, 3 values of 2, and 3 values of 3. So 2 1s, 3 2s, and 4 3s. Without a histogram, we run explain. We're going to explain select star from our table where x is greater than 0. And remember that all our values are greater than 0. The optimizer without a histogram is going to go, well, we know the table has 9 rows in there, and I'm going to guess that I know where it is. I know where I'm going to have to read at least a third of the table to get the information. Well, we know that all the values are greater than that. So the filtered value here is kind of a estimated percentage of the table rows that need to be looked at. Now, where the histogram shines is we go ahead and create a histogram on our table with 3 buckets. Now, when we run the explain on there, it knows where all the data is. It it says, yeah, I know where I'm gonna have to go. I'm gonna have to get all the data. Now, if you run explain analyze, we'll come back and give you the actual costs and the time that it takes to run everything. Now, I'm kind of running down in my last 5 minutes before I go to a dedicated Q&A. By the way, if you do have questions, please pop them in the Q&A. There are other tweaks you can do to speed things up. You can use explain to see what your query is doing. Are there file sorts, full table scans, temporary tables? Do the join orders look right? The configuration side, are the buffers and caches big enough? Do you have enough memory? Are your disks just slow? That still happens these days. Something you do is we've made 2 changes to locking in MySQL 8.0, no wait and skipped lock. This might help you rechange the way you use your data. For example, here, we want to buy some concert tickets, and we're going to start a transaction, and we're going to go out and select a seat and a row, and we're going to grab the cost while we're at it from a table called seats. And what we want to do is we're looking for seat numbers 3 and 4 in rows 5 and 6 that are not booked. Now we want to grab them because we want to book them. And this will automatically skip over the locked tables. Before this, the database would wait until those rows became available. Lock no wait basically says if there's nothing there, immediately return to me. Now, other ways you can do, oops, I got a question. Let's see. Is there a link to the 90-minute full version of the talks that you have mentioned in the beginning? Yes, I'll have to look it up though, and I will post it on my Twitter at Stoker. Let me type that. Okay, so get that out there. Okay, other fast ways, resource groups, optimizer hints, partitioning. And resource groups, this is where you can dedicate virtual CPUs to certain classes of queries. In this example, we create a batch group, and we dedicate 2 CPUs and set it to a low thread priority. So every time we set a resource group batch in a series of commands, or we put in this optimizer hint, the stuff here in magenta, the optimizer knows to set those to go to that lower priority. Optimizer hints. These are little comments you can put into your query. So like, it's better to join T1 to T2 than T2 to T1. The optimizer will see this. Hopefully it will know that you know what you're doing, and away you go. Partitioning, you can actually divvy up your data over various partitions if you're running InnoDB or our NDB storage engines. So if you want to keep the data for the last quarter on partition A, stuff for the previous 3 quarters on another partition, stuff for years past on yet another set of disks, you can do that. The optimizer knows about that and knows how to go grab it off the various partitions. Okay, this is an interesting example of what the optimizer actually does. This is our query. We're going to go out and we're going to select city.name from the city table, country.name from the country table. Now these 2 tables have been set up so that city.country code is the hook into the country table using the code column. And we only want to know the city names for GBR, where the country code is equal to GBR. So once again, we're looking for city name, country name from these 2 tables. That's how we're matching them up. And this is a qualifier. So if we run explain on this, it comes back and tells us, yes, you're doing this on 2 tables, country and city. Notice that country is a smaller table, so it's going to kind of look at that first. Now, the actual query plan that we get is select world.city.name as name. World, by the way, is a schema or database. We have all this. And United Kingdom as name. So that country.name, it's automatically rewritten that for us. So it's already done some magic for us, even on a very simple query such as this. If we run explain analyze, it will go out and give us the real cost of how everything runs. Now, oops, there was my timer. Let me run through this one slide. learning to read this is kind of hard. I have some books that I will get to that I recommend that you're going to have to, these are exercises I run through. By the way, where else to look for information? The MySQL manual, forums.mysql.com. Also, we have a MySQL community Slack. Please join. You're part of the community now that you've sat through this. Great book. You need this book. Jesper Wisberg Crow used to work at our support group. The book's about 5 inches thick. I'm on my second rereading of it. I'm still learning stuff. Very interesting. This is an older book. If you're running older versions of MySQL, it's getting dated along in the tooth. A lot of things have changed. This is my book if you're using JSON and MySQL. By the way, if you are a startup, Oracle can help you. They have this wonderful program where they give you lots of credits and lots of help. If you are a startup, please take a look at that. And with that, there's my contact information. And once again, the slides are there, and I will get the longer link out there for the Q&A. And with that, I've got the Q&A window if there's any questions. I can say more about the benefits of histogram versus index when your data doesn't churn. I don't follow logic. Okay, indexes are designed. I used to be able to use the library reference card system, but very few libraries actually have those anymore where they actually have cards. Histograms, you kind of divvy up your data in buckets so that you know the A's are over here, B's are over there, and all that. Indexes, as soon as you insert a piece of data, there's a new index entry in there. What I mean by don't churn is indexes are better when you're adding or changing a lot of data. Histograms, you make the histogram once. You throw them in the bucket A, and it doesn't know that if you change the last name from Adams to Jorgensen that the name has changed. You'd have to rerun the histogram on that. I missed in the output. Since I answered that. Okay, the second question I have, I missed in the output explanation of what is the cost. Well, cost-based optimizers have been around for 40 some odd years, and the idea is that you want to get the data back from your query at the lowest cost being disk reads, because disk reads are very, very slow. Disk reads are 100,000 times slower than reading out of memory, so you kind of go for the worst case scenario there. Let's see. Thank you, Carl and Catherine. If there's any other questions, I'll be here for a while. And if you have any questions, please do not hesitate to ping me, david.stokes@Oracle. I have a blog at elephanttdolphin.blogspot.com. I'm at Stoker on Twitter. Once again, please join the MySQL community Slack. A lot of our engineers hang out there. So if you have a question about the optimizer, the new shell, replication, anything like that, you're more than welcome to join us. And back to Nixie and Vance.
Thank you very much, David.